Welcome to Advanced Linear Algebra. Today we are going to explore a fascinating and deeply fundamental concept called the transpose of a linear transformation. This mathematical tool allows us to run rules in reverse, bridging the gap between different spaces. By the end of this lecture, you will understand both the geometric intuition and the algebraic mechanics behind it. Let us start with an analogy. Imagine a factory machine that takes raw materials and builds finished furniture. The forward building process is a linear transformation, T. Now imagine an inspector who assigns a final dollar value to the finished furniture. This inspector represents a linear functional, and the set of all possible pricing rules is called the dual space. What if we want to know the exact value of the raw materials before they are built? We need a way to pull that pricing rule backward. This backward pulling process is exactly what the transpose does. Now that we understand the intuition, let us look at the formal definition. The transpose map takes a function that evaluates outputs and turns it into a function that evaluates inputs. In this formula, T transpose is the new operator we are defining. The symbol G represents a specific linear functional chosen from the dual space of the target. The variable x is a vector in the original starting space. This equation tells us that evaluating the transposed functional on an input vector is exactly the same as transforming the vector first and then evaluating the original functional on that result. Before we move on, let us see this with a concrete example. Suppose we have a linear transformation from R2 to R2 and a linear functional g defined in the dual space of the target. Our goal is to find the explicit formula for the transposed functional. We rely entirely on the fundamental definition. We know that applying the transposed functional is the same as transforming the vector first. So our first step is to substitute the output of the transformation directly into the functional g. Continuing with our calculation, we now apply the specific rule for our functional g. The rule says to multiply the first input by 5 and subtract the second input. We substitute our transformed coordinates into this rule. After distributing the constants and combining like terms for x and y, we arrive at our final expression. This transposed functional is a brand new rule that takes an input vector and directly outputs a scalar, completely bypassing the intermediate target space. This physical interpretation shows the direct bridge we have built. Having calculated the transpose, let us visualize what just happened. This diagram summarizes the entire concept. On the left, you see the original transformation, pushing vectors forward from space V to space W. On the right, the transpose pulls linear functionals backward from the dual space W star to V star. Notice how both paths ultimately point to the same scalar output in the field F. This scalar output remains the anchor point that forces these two directions to perfectly balance each other. Now that we have a clear geometric picture, we can connect this abstract concept to matrices. One of the most beautiful results in linear algebra is how the transpose of a linear transformation relates to the standard matrix transpose. To do this, we represent our forward linear transformation as a matrix by choosing a basis for our starting and target spaces. We then use the corresponding dual bases to find the matrix representation of the transposed transformation. This connection is vital for computation. This brings us to a powerful formula. If A is the matrix representation of our original transformation, then the matrix representation of the transposed transformation, which we call B, is simply the standard matrix transpose of A. This means the abstract concept of pulling a functional backward perfectly matches the mechanical process of flipping a matrix along its diagonal. As the dimensions of the vector spaces increase, this relationship ensures that algebraic matrix operations always have a rigorous geometric meaning. If the entries of A change, the entries of B adapt instantly. Before we prove this matrix property, let us verify it using a previous numerical example. We want to find the standard matrix representation of T. We build the matrix A by plugging the standard basis vectors into our transformation one by one. The first basis vector maps to 1, 3, which becomes our first column. The second basis vector maps to 2, 4, which becomes our second column. This gives us a complete forward matrix A, setting us up for the next step. Continuing our verification, we find the matrix transpose of A by swapping its rows and columns. This transposed matrix tells us how to map functionals backward. We represent our functional G as a column vector, 5 and -1. When we multiply our transposed matrix by this vector, the matrix multiplication yields 2 and 6. These are exactly the coefficients we found in the first example. The matrix transpose perfectly encodes the backward pulling action, confirming our physical interpretation of the dual space. Now that we have seen it work, let us prove why it works. We start by defining the matrix A for the forward transformation, which produces a linear combination of the target basis vectors. Similarly, we define the matrix B for the transpose transformation using the dual bases. To find out what the entries of B actually are, we evaluate both sides of our transpose equation on a specific basis vector from the original space. We begin by expanding the right side. This chunk of the proof establishes the foundational equations we need to connect the two matrices, setting the stage for the algebraic collapse in the next step. Continuing the derivation, we look at the dual basis functional on the right side. By definition, it evaluates to 1 only when the indices match and 0 everywhere else. This causes the entire summation to collapse down to just a single term, B sub kj. Now we must evaluate the left side of the equation using a fundamental definition of the transpose. We substitute the known linear combination for the transformed vector into the functional G. This step is crucial because it links the abstract functional evaluation directly to the matrix entries of our forward transformation. We are now perfectly positioned to simplify this expression and find our final result. For the final steps of our proof, we use the fact that G is a linear functional to pull the summation and constants outside. Just like before, the dual functional evaluates to 1 only when the indices match, which collapses this summation down to A sub jk. Since we evaluated the exact same expression in two different ways, the two results must be equal. This proves that the entry in matrix B is exactly the transposed entry of matrix A. The intuition here is beautiful. The geometry of dual spaces naturally produces the algebraic matrix transpose. We have successfully derived the theorem from first principles. So we have proven that the matrix transpose property holds. This brings us to why this abstract backward pulling matters in the real world. It is the mathematical foundation for many advanced applications. In quantum mechanics, the transpose is used to move operators from physical states to observable measurements. In machine learning, the famous backpropagation algorithm used to train neural networks relies entirely on the transpose to propagate error gradients back to the input weights. Without it, we could not learn from errors. Let us summarize what we have learned today. The transpose of a linear transformation acts as a bridge between dual spaces, seamlessly converting a rule that evaluates outputs into a rule that evaluates inputs. We saw how the fundamental definition ensures a perfect balance, and we proved that this abstract operation corresponds exactly to flipping a matrix along its diagonal. You now have the tools to analyze complex systems not just by where they go, but by how their results are measured. Great job completing this topic.